My name's Sanjeev Gupta. I'm a geologist in the Department of Earth Science and Engineering at Imperial College London, and I'm also a science team member of NASA's Mars Science Laboratory, the Curiosity rover mission, the latest mission to land and rove on Mars. This week we've published the first science paper resulting from the mission that reveals evidence for ancient water flow on the surface of Mars. In November 2011, I was really fortunate to witness the launch of MSL, Mars Science Laboratory, on board an Atlas V rocket from Cape Canaveral. I took this image as the rocket was leaving Earth's atmosphere. MSL then took a 9-month journey before arriving at Mars. Curiosity landed on Mars on the 6th of August 2012 in an audacious landing sequence dubbed the 7 Minutes of Terror. Here, in this image, you can see the rover actually being lowered onto the surface of Mars by a series of nylon tethers from a rocket-propelled landing system. Curiosity landed in a site called Grail Crater, which sits near the equator of Mars and also sits astride what's called the planetary dichotomy, a major change in topography from the higher southern highlands and the lower northern lowlands. The crater is 150 kilometers wide, and the site was chosen for Curiosity's landing because, intriguingly, in the center of the crater there is a mountain almost 5 kilometers high that is comprised of sediments. Now, sediments record the ancient surface environment on planets. So on Earth, for example, geologists analyze sediments and sedimentary layers as a record of changing environmental conditions. And we can analyze these rocks and reconstruct whether the rocks were deposited in the sea or by ancient rivers or ancient deltas. The aim for Curiosity is to analyze these ancient rock layers in Gale Crater and reconstruct the ancient environments to find out if they were deposited under watery conditions, what the chemistry of those sediments are, and whether those sediments laid down billions of years ago in Mars's past might have preserved an ancient habitable environment. That's an environment where life might have formed and been preserved. With the amazing landing system Curiosity had, we were able to define a very narrow area for Curiosity to land. So you can see here in this image, the blue ellipse shows you the landing ellipse. And Curiosity, for safety reasons, of course, landed in the flat plains between the crater rim and the mountain, the 5-kilometer high mountain in the center of Gale Crater, which is called Aeolis Mons, or Mount Sharp. The green diamond actually shows you Curiosity's landing site. So Curiosity is quite an amazing robot. It has a lot of instruments, so it's a field geologist and also a field geochemist at the same time. The geologist tools are an array of cameras, and then there's a whole series of geochemistry tools to analyze the mineralogy and the elemental makeup of the Mars soils and rocks. Myself, I mainly use the imagery generated by the Mastcam cameras that provide large-scale images, and also the hand lens camera, which it can take really close-up pictures of rocks. But it can also do something that's really amazing. It can actually point, the Marley camera, the hand lens camera, is actually attached to the arm of the rover. It can actually look back on itself, and like you might point your iPhone at yourself and take a picture of yourself, it can actually take a self-portrait. And here you can see one of the first self-portraits taken by the Marley camera, showing you the amazing vistas of Mars, but also a beautiful image of the rover itself. So within days of landing at the surface of Mars in Gale Crater, our instruments got working, particularly the cameras, and here you can see a beautiful color, the first color mosaic taken by the Mastcam cameras. You can see in the distance Aeolis Mons, or Mount Sharp, that 5-kilometer higher mountain. And then in front of the rover, you can see this gravel plain extending out for a long distance. Now, this gravel plain is actually comprised of clasts, rock clasts, but these are angular rock clasts, and most of these have resulted from hundreds of thousands of impacts, so meteorite impacts on the surface of Mars that impact the surface and break up rocks, producing these angular clasts and also weathering processes. In addition, we were able to turn around and look in the other direction and take a picture of the crater rim. This is really remarkable because it's the first time that a landed mission on Mars has actually been able to take pictures of quite pronounced relief. And here you can see in this hazy shot with the dust in the air, the rim of the crater, which we know from orbital imagery actually has erosional catchments, so evidence of erosion by water sculpted into the surface. So one of the reasons we landed in Gale Crater not only was because we had this thick pile of sediment that we could analyze, but also we knew from analyzing orbital imagery that we saw canyons carved into the rim of Gale Crater. And in this image, you can see a topographic map of the landing area, and you can see a canyon, which we've named Peace Vallis, incised into the crater rim. And where it emerges into the plains within the crater, we can see a elongate, flaring out feature that's topographically slightly higher. And this on Earth we call an alluvial fan. And on the surface of this fan in Gale Crater, we can actually see the remnants of ancient channel-like features. So we knew we had some idea that there might be evidence in our landing area of past water flow. Typically, alluvial fans on Earth occur where canyons emerge from mountains and where the flow velocities abruptly decrease as you go onto the flat plains. The sediment abruptly drops out and gets deposited as a lobe of gravel and sand. So what we knew was that the landing ellipse actually occurred at the downstream limits of this fan. So we made a prediction that within the landing ellipse, we might find sediments that were associated with this alluvial fan. Often missions are serendipitous, and we were really lucky where we landed. This image actually shows you the vicinity of the landing site, and where you can see the word Goulbourn here, that's actually the landing site, and the blue areas are areas where dust has been removed from the Martian surface by the retro rockets of the landing system. And then you can see a series of outcrops on this map called Link and Hotter, and these were our most exciting findings within the initial days of the mission. So this image shows you the Goulbourn locality, and here actually it was the descent rockets that actually cleared the dust to make this outcrop available. And what was very interesting here is that we're not actually looking at loose gravel on the surface of Mars. What you can see is clearly lithified layers that are subhorizontal. And then what was remarkable was that we could actually see pieces of rock clasts actually embedded in those rock layers. If you look at the close-up to the left-hand side, bottom left-hand side, you can see a variety of different clasts actually embedded in that rock layer. And we started trying to understand what this rock type meant, what we were actually looking at. And it wasn't until we started getting to the next outcrops, Link and Hotter, that we really got a sense of making an interpretation of these rocks and getting really excited about what it told us about the ancient Martian past. On this image, on the left-hand side, you have an image of the Link outcrop. What you've got is a rock layer, and you can see a cut face through that rock layer. It's not very thick, in fact, but if you look inside, you can see that it's actually made up of lots and lots of different clasts that are up to 1 centimeter in diameter, and you can see that the clasts, or the pebbles in this rock layer, have different colors. So that means that they probably have different lithologies. They're made up of different mineral types. So you can see a dark layer, a dark pebble in the center, and if you go to the top left, you can see clasts that are white in color. Now, if you look at that dark clast, the most prominent clast, towards the center right, you can see that its outline is actually not angular. It's actually slightly or moderately rounded. And this is very interesting because, as I said, most of the clasts on the Martian surface today that form these gravel plains are highly angular because they've been made by constant impacts and breaking up of rocks by meteorites hitting the surface. Whereas here, this tells us that this is a rock layer that was formed long before the present day surface. So it's an ancient rock, and that it's made up of rocks or clasts, pebbles, that have been rounded through some flow process. On the right-hand side, you can actually see an image of pebbles from an ancient alluvial fan in the Atacama desert in Chile. And you can see very clearly in this, it's at a similar scale to the Martian example. And again, you can see how the clasts are relatively well-rounded. Now, this rounding happens when clasts travel down a river. They're constantly bumping into each other, and as they hit each other, corners of the clast get knocked off, and the surface of the clast, the circumference of the clast, actually gets progressively rounded as you go downstream. And on Earth, this is a sure sign of transport by water processes. In this image, this is the final outcrop, hotter, and this is a close-up, and you can see the rock layers that are slightly tilted to the right-hand side. In the circle, you can see quite a large clast, a couple of centimeters in diameter, and again, you can see that very rounded perimeter. And then you can see in the rest of the rock body that the clasts are all huddled together, all clustered together and touching. And again, this is a sure sign that the clasts have basically been rolled along a riverbed in a process that we call bedload transport. What's amazing is that we can use physics to reconstruct something about the flow dynamics of these ancient rivers on Mars by applying mathematical equations derived from studies on Earth. So one of the things we've been able to show, because we know the size of the clasts, we can calculate approximately, and it's very approximate, how fast the flows were. And it's been estimated by the science team that the flows at this location, at this site where we've landed, the water flows were probably flowing at walking pace, for example, and that water depths were perhaps knee-deep. Of course, you might say that other processes could have moved these clasts. So the most prominent flow process probably on Mars is wind action. There's plenty of evidence for wind-blown sand dunes on the surface of Mars. But what we know by looking at these images is that clast sizes are much too large to be transported by wind action. So that rules wind action out and really only leaves water as the primary flow process to explain these gravel beds. And here in this image that I recently took on holiday is a beautiful slide of some ancient river gravels from alluvial fans in Crete, and you can see the nice layering that you get in these sediments, in these ancient sediments, and you can see the nice rounded character to the clasts here. And we know that these clasts were clearly deposited by flowing water at the toes of an ancient alluvial fan, and they look remarkably similar to the gravel deposits that we're seeing on the surface of Mars in Gale Crater. So this image shows you a map of the alluvial fan shown by the contours in Gale Crater. The yellow star shows you our landing site and the location of these ancient river gravels. And so one interpretation is that the gravels that we see were actually transported by water flows down the alluvial fan. You can see the black arrow shows the direction of flow, and ended up being deposited where we see the yellow star. But that's not the only interpretation. Our studies were made in the early days, and we're constantly on the move, and because it's a reconnaissance mission, we can't work everything out. So an alternative interpretation potentially is that these gravel clasts actually are alluvial fan deposits actually derived from Mount Sharp or Aeolis Mons. So that's the giant mountain in the center of Gale Crater. And we hope in the next year or so, as we drive towards Mount Sharp, we'll be able to resolve this problem.